Good morning, everybody. Previously, we have discussed about the controllability and observability. So today, I'm going to show you guys another topic related with realization of a transfer function. So we can see it here. If we have a state space representation x dot equals ax plus bu, y equals cx plus du, and through Laplace transform, we can get the transfer function g of s as matrix C times Si minus A inverse times B plus D matrix. Okay, so we have learned this many times that the state space representation is equivalent to this transfer function. However, normally we're facing another problem, which is if we know the transfer function of the system, is it possible for us to find a state space representation, which is a backward problem? Okay, we called this problem as realization problem. Why we need to have the realization problem solved? The reason is in your undergraduate class 3413, we have shown you you can generate a Bode plot of a system. There are two ways for you to generate a Bode plot if you don't know exact system. First one is you have that instrument. When you have different frequencies of input, you measure the output of the system, and then you got the ratio of magnitude and phase delay for each frequency. Then you can draw the Bode plot of the system. If you draw the Bode plot of the system, you can easily get the transfer function of the system. So right now for a state space representation, how can we get this ABCD matrix? And also we can say that transfer function is easy to obtain for modeling, but ABCD, if you don't know exact physical system, it's very hard for you to determine the parameters. But however, for controller design, if you know the ABCD format, it's much easier for you to design a controller. So with all of this consideration, we need to look at realization problem. So we define realization is a process to obtain state space model ABCD from the transfer function. We're going to illustrate the procedure with a second order motivating example here. So here we have g of s equals c1s plus c2 divided by the numerator s squared plus a1s plus a2. And starting from here, we want to find a corresponding ABCD formats for this transfer function. Okay, so the first thing we need to know that if we define x1 of s, which is going to be s multiplied with u s squared divided by s squared plus a1s plus a2, we define it as a Laplace transform of x1 of t. Why we want to do this one is, first, we want to look at what's the effect of the parameters a1, a2, the parameters in the denominator affect the ABCD representation. Okay, and then further, we define that x2 of s is going to be u over s squared plus a1s plus a2, and then this x2 of s is going to be the Laplace transform of x2 of t. Okay, this capital U represents the input of the system. So if we have such definition, we can see that x1 of s is going to be s times x of 2. And meanwhile, by the definition of Laplace transform, we know that s represents a differentiator. Then we can see that x1 of t is going to be x2 dot of t. Okay. One step further, okay, if we look at sx1, which is going to be s squared times u divided by s squared plus a1s plus a2. Okay, and then because previously in our Laplace transform transfer function, we always said the numerator, the degree of the numerator is going to be less or equal to the degree of the denominator. So in this case, we have exactly the same degree as squared in the numerator and s squared in the denominator. Okay, so let's look at how can we represent this one. So this s squared u is going to be exactly s squared plus a1s plus a2 times u minus a1su minus a2u. And then we can see this one is equivalent to u minus a1 multiplied with su divided by s squared plus a1s plus a2, which is going to be, by the definition, it's going to be x1 of s minus a2 u over s squared plus a1s plus a2. And then you can see the red block show you this is going to be, this was defined as x2. And then through inverse Laplace transform, we can see sx1 is equivalent to x1 dot. And then u of s will give us u of t. And then here we have minus a1 x1t minus a2 x2t. So based on the two equations we showed before, the first equation is x1 dot equals x1 equals x2 dot. And then the second equation is x1 dot equals u minus a1 x1 minus a2 x2. Then we can rewrite this as a state space representation. Here we can see that the A matrix is negative a1, negative a2, 1, 0, and the B matrix is 1, 0 as a column vector. Okay, so here this motivating example shows us what is going to be the relationship between the denominator parameters a1, a2, and the A matrix. Then the second question we need to look at is where does that C matrix come from? As was shown before, y of s is going to be g of s multiplied with u, and then we have c1s plus c2 divided by s squared plus a1s plus a2 times u. So it's equivalent to c1 times su divided by s squared plus a1s plus a2 plus c2 times u over s squared plus a1s plus a2. And by the definition, we can see these two red boxes are defined as x1 of s and x2 of s. If we further take the inverse Laplace transform, our y of t is going to be c1 x1 plus c2 x2. And this gives us the output matrix here, with the C matrix equals to C1, C2 as a row vector. Okay, and then let's have an illustration of what does this, where do the parameters go from the transfer function to the state space representation. We can see for the denominator a1, a2, they map to this A matrix, where it's negative a1, negative a2, and then you have 1, 0 in the second row. And for the C matrix, it was mapped to the output as C1, C2, where C1 is going to be the parameter here, C2 is here. Okay. So in general, we will have a higher order system where we have g of s equals c1 times s to the power of n minus 1 plus c2 s to the power of n minus 2 plus until you have this constant cn come out. Remember here we have c1 times s to the power of n minus 1. The degree of the numerator is still less than the degree of the denominator. So in the denominator we have s to the power of n plus a1 s to the power of n minus 1 until you have an. Okay, so the general realization of this system can be written as a equals negative a1, negative a2 until you have negative an, which are all the parameters related to the power of s to the power of n minus 1 until you have s to the power of 0. And then the lower part of A matrix is going to be the identity matrix, but it's going to be n by 1 to the lower left bottom. And then all the other elements will be 0. For B matrix, it was 1 on the top, and then all the other elements will be 0. For the C matrix, it will be C1 from the highest order of the S power to the lowest order of the power of S. And because here we have the degree of the numerator less than degree of the denominator, we have matrix D, which is going to be 0. Okay, so I will give you several examples here. So our first example is going to be S squared plus 5 divided by S to the power of fifths plus 5. So if we rewrite this transfer function by the order, we can see the denominator will be s to the power of fifths plus 0 s to the power of fourths plus 0 s to the power of cubic plus 0 s squared plus 0 s plus 1. And then we can do the same thing for the numerator. It's going to be 0 s to the fourth order plus 0 s cubic plus s squared plus 0s plus 1. And then we will rewrite the A matrix according to the parameters 0, 0, 0, 0, 1. And then we can rewrite negative A1, negative A2, negative A3, negative A4, negative A5 like this one. Because the fourth order to the first order, they are all 0. We can see 0 here, and then the last term is negative 1. And then here, if we look at the lower bottom of this, we can see it's going to be an identity matrix here, and we can see the rest part are all of 0. Because the denominator order is 5 to the order of fifth degree, so we can see that the N matrix is 5 by 5. Okay, and meanwhile your B matrix is going to be 1 on top, and then all the other elements will be 0. For the C matrix, we're going to match the parameters here. So we can see that this 0 is coming here, okay, and this 0 is coming here, and this 1 is coming here, this 0 is coming here, this 1 is coming here. So we have the C matrix as a 1 by 5 matrix, which is 0, 0, 1, 0, 1. Okay. So this second order and fifth order example shows us how to match the A, B, C, D parameters from your numerator and denominators of the transfer function. So next, we're going to verify if we really have such system, will the transfer function obtained from C times Si minus A inverse times B be really the original transfer function? So I'm going to use a 3D case to verify it. Okay, so here is the transfer function g of s, which is going to be c1s squared plus c2s plus c3, and divided by s cubic plus a1s squared plus a2s plus a3. By our previous realization format, we see that my A matrix must be negative a1, negative a2, negative a3, and I have n by 1. Here is going to be 2 by 2 identity matrix, and then all the other elements will be 0. And my B matrix will be 1, 0, 0. My C matrix will be C1, C2, C3. And I want to verify whether the transfer function I can obtain from C Si minus A inverse times B will be my original transfer function g of s or not. Okay, so we're going to check this one. When we calculate C Si minus A inverse times B, which is going to be C1, C2, C3 multiplied with S plus A1, A2, A3, negative 1, S0, 0, negative 1, S inverse times 1, 0, 0. Okay, so the first thing we want to see is if here I have a 3 by 3 matrix, and then I multiply with the vector 1, 0, 0, it's going to be, I will sample the first column of this matrix. But remember, it's the inverse. So the inverse matrix is obtained by the adjacent matrix divided by the determinant of Si minus A. So the adjacent matrix, when we look at it, the first element is going to be when I cross the first row, first column, where is this red cross, I will have the determinant of S0, negative 1s. When I calculate, it's S squared. And the second element, which is shown as the pink one here, is going to be the determinant calculated by while I remove the first row, second column. Then when we calculate the determinant of negative 1, 0, 0s, we'll have negative s come out. But remember, it must be multiplied with negative 1 times negative 1 to the power of I plus j. So because it's first row, second column, I plus j is 3, negative 1 to the power of 3 is negative 1. So I still get s come out. Okay, and then the last element, which is represented by the adjacent matrix, when I remove the first row, the third column, remember it's first row, third column, I plus j is 4. So negative 1 plus, to the power of 4 is positive 1. And then when I calculate, it's 1. The rest of the elements, no need for me to calculate because I'm going to multiply with 1, 0, 0. I will only sample this first column. Okay, and then when I do that, I will get C1, C2, C3 multiply with S squared S1, okay, divided by the determinant of Si minus A. When I calculate this, you can see that easily the determinant is going to give me exactly s cubic plus a1 s squared plus a2s plus a3, and then c1 s squared plus c2s plus c3 will be the numerator. Then we can verify that through the C Si minus A inverse times B operation, I really got my original transfer function as shown before. Okay. You may ask me why the determinant of Si minus A inverse is going to be this one. I think I showed you once in my last lecture, which was decomposition problem. If you don't get it, you can let's practice after the class, or you guys can visit me during my office hour. Okay. Okay, the following question is, previously when we have that transfer function, we always assume that the numerator, the degree of the numerator is going to be less than degree of the denominator. In some special cases, if the degree of the numerator is going to be equivalent to the degree of the numerator, we have the D matrix come out, which is not a zero value. So let's see this example. So we have G of S, which is going to be D0 S to the power of n plus D1 S to the power of n minus 1 until you have Dn, and then the denominator will be S to the power of n plus A1 S minus 1 until you have the term An come out. And when you do the polynomial division, we showed you at the beginning of the semester, you can see here we'll have D0 come out, and then the denominator won't change, but the parameter of the numerators will be changed. You will have C1 S to the power of n minus 1 until you have Cn come out as the parameters of the numerator. Then for the second part, which is going to be represented or realized as G hat of S. Okay. How to calculate the G hat of S is just the polynomial division of the numerator divided by the denominator. You got C1, C2, and then when you got C1, C2 in the and Cn in the numerator, you have got the polynomial of the denominator. It's going to be the same realization as we showed before. So starting from G hat of S, we can have a realization of A, B, C matrices, and then we can see that G hat of S is going to be GS minus D0, and then we have that D matrix as D0 come out. Okay, I will show you one example here. So here we have G of S equals S squared divided by S squared plus 1, and then we can see that it's going to be 1 plus G hat of S, and G hat of S was calculated by G of S minus 1, and then we can get this S squared minus 1 in the numerator which is going to be 1 over S squared plus 1. And then based on this, we can have the ABC matrix realization as 0, -1, 1, 0. B is going to be 1, 0. C is going to be 0, 1. Okay, and then the D matrix here is going to be just one scalar 1. Okay, so far we have showed you guys how to realize a system with state space representation based on the transfer function. Okay, and after we have the state space representation, as we showed before, we need to check whether your system is controllable or observable. So let's look at the current realization. What we have is my A matrix is going to be -A1, -A2 until I have -AN, and then in the lower left bottom I will have an identity matrix and all the other elements will be 0. And my B matrix is going to be 1, 0, 0, 0. Okay, so what I want to see is whether this B, A, B, A square B until I have A to the power of N minus 1B is going to have full rank or not. Okay, so let's check it first. My B is 1, 0, 0, 0. My AB, when we look at it, we're going to sample the first column of it, which is going to give me -A1, 1, 0, 0, 0. And then A times my AB is going to give me the combination of this A matrix, the first two columns. Then when you look at it, I'm going to have A1 squared minus A2, -A1, 1, 0, 0, 0. Okay, and then my A cubic B will be the combination of first three columns. Then when we look at this rank BAB, A to the power of N minus 1B matrix, we can see it's exactly an upper triangle matrix which has full rank N. So the conclusion is, with the previous realization format, we have a controllable realization of the system. Okay, so if system is controllable, the following question is the system with the realization ABCD observable or not? We'll check it again. So when we look at this example we showed before, so here we have S over S squared plus S, and then by complete all the parameters in this format, we can see that the A matrix is going to be -1, 0, 1, 0, B is 1, 0, and C matrix will be 1, 0 also. So we have verified this is a controllable realization. So let's look at the observable rank. So if we check the rank of C times A, C times A squared, we can see that here, because it's 2 by 2, I only need to check C and C times A. So C is 1, 0, C times A will give me -1, 0. You can see that the rank of the system is going to be 1. So with this controllable realization, my system representation is not observable. Okay, then there are two questions need us to answer. What is going to be an observable realization, and what is going to be a controllable and observable realization? So let's look at the first question. How can we have an observable realization? So if we have the controllable realization as shown here, my AC, BC, CC will give me the transfer function here, okay, which is going to be CC times SI minus AC inverse times BC. Because my transfer function is going to be a scalar because it's a single input, single output system. So the transpose of my transfer function is still going to be the same scalar, which will give me G of S equals G transpose of S. So if we look at the G transpose in this format, what we're going to have is going to be C SI minus AC inverse BC transpose, which will give me BC transpose times SI minus AC transpose inverse times CC transpose. Okay, so if we define another matrix realization, which is going to be CO equals BC transpose, AO equals AC transpose, BO equals CC transpose, then the transfer function is going to be CO SI minus AO inverse times BO, which is going to be exactly the same transfer function. Okay, and then with this new realization, I want to check its observability again. Remember, right now your CO matrix is the original BC controllable matrix B transpose. Okay, so what we have is this new realization x dot equals A0x plus B0U, y is going to be C0x. Okay, and when we look at the different representation of the system, of different realization of the system, we can see that definitely realization is not unique. So here at least we found two realizations already. One is a controllable realization. We have AC, BC, CCD, and the other one is going to be AO, BO, COD. Okay, and I want to check the observability of the second realization RO. So because AO is going to be AC transpose, BO is going to be CC transpose, CO is going to be BC transpose. So when we check the rank of the observability, it's going to be CO times AO until you have CO times AO to the power of n minus 1, which is going to be same as BC transpose times AC transpose, BC until you have BC transpose times AC transpose to the power of n minus 1. It's going to be the same thing as your BC, AC, BC until you have AC to the power of n minus 1 times BC. And we have verified that the rank of this BC, AC, BC pair is n. Then we can show that we have the full rank of this observability matrix. So AO, CO is an observable realization. This is called the dual theorem. If we have a controllable realization and then we have the transpose of AC as another realization and the transpose of CC as your B matrix, transpose of BC as your CO matrix, then we can have a controllable realization. So I show this format here. We can see that with the same transfer function, we can have another realization where AO is going to be negative A1 to negative AN as the first column, and then in the upper right column, you can have n by 1 identity matrix and all the other elements will be 0. So your B0 is going to be C1, C2 until you have Cn, and your CO is going to be 1, 0, 0, 0, which is your previous controllability matrix B. This is your previous output matrix C, and here is the transpose of your previous AC matrix. Okay, so the last question we want to answer is when we can obtain controllable and observable realization, if there exists such realization. Okay, so the first thing we say, a minimum realization is both controllable and observable. What is minimum realization? The definition of the minimum realization is for all the realizations Ri of G of S, because we showed for same transfer function, for one transfer function, you may have many times or many different realizations. And the minimum realization says if there exists Rm, which guarantees that the dimension of Rm is going to be less or equal to all the other dimensions of the other realizations, then this Rm is called the minimum realization. So we are really looking at the dimension of the realization, which is going to be majorly determined by your A matrix. Okay, so I'm going to show this example here. So with this transfer function G of S equals 1 over S plus 1, and the first realization is my A1 is going to be negative 1, my B is 1, my C is 1. Okay, and then I can see that clearly I can get this transfer function 1 over S plus 1. So the dimension of the realization is 1. My second realization is I have A2, which is going to be negative 1, 0, 1, 0, and my B2 is 1, 0, my C2 is 1, 0 also. So when you check this one, you can see the second realization also gives you this 1 over s plus 1. But the realization is dimension 2. And meanwhile, A3, you can have another realization, which is going to be the transpose of this A2 realization. We can see that it's going to be negative 1, 1, 0, 0. Again, B3 is going to be 1, 0, C3 is going to be 1, 0. You can see that the third realization is also the third realization also gives you the transfer function 1 over s plus 1. But the minimum realization is the first realization. Okay. So with all of this information presented, the question we want to finally answer is how to make sure a realization is minimum. Another thing we can say is how to obtain minimum realization, or what is the condition for minimum realization. We're going to illustrate it by the following lectures.